let me share my screen first. Yeah, I hope you can see the slides right now.
Yeah.
Yeah, I'm sorry that the title is a little bit different from the title that in the advertisement. So I'm still going to talk about the similar material, but I reduced the amount of the new results in the sense that I'll mainly briefly introduce this definition of stability manifold on a triangle category, which was introduced by Bridgeland about 20 years ago, which I thought it's a very elegant construction and has only been aroused interest in the algebraic geometry side, and I hope there could be some parallel development in the algebraic topology side. So before, yeah, great. Before we go to the main content, let me make this probably redundant remark for all the algebraic topologists audiences here. So you know, you all live in the real world, but I'm a complex algebraic geometry. So all of my stuff are over the complex number field C. So in particular, when I say a variety, it all means this complex variety. And in this talk, all of varieties are smooth, so it's harmless to think them as complex manifold, whatever you want. And also, when I say a vector bundle, it always means a homomorphic vector bundle. And another stuff is the tricky stuff. So the dimension in my talk are always doubled. So when I say a curve, I actually means in the real world a surface. And when I say surface, I use this so-called K3 surface a lot in the talk. It means fourfold, and threefold means sixfold, and fourfold actually means eightfold, so on and so forth. In particular, for example, this curve, the main character of that is elliptic curve. By an elliptic curve, I mean my elliptic curve is this, or topological, it's this. Yeah, Riemann surface, when you call it. And also another thing is one of the main objects in this talk is this so-called triangular category. I hope you also use this concept a little bit in your research. But if that's not the case, that's not a very good thing, because I'm not going to give the detailed definition of it. And another thing is, if you use this triangle category, you may have your own example. But in my case, all of my triangle category are this BB co X, which is the bounded derived category of coherent sheaves on the variety X, where X is a manifold. So if you have no feeling or no idea it is, so just think about when I write this thing, the objects in it. So it's a category, it's triangle category. The objects in it are just the complexes of vector bundles, modulo some homotopy equivalents, and the homes are just the homes between complexes, modulo out some homotopy equivalents. But anyway, that's a rough thing. All right, so this is a remark. Now let's go to the mathematical contents. So the first part is we're going to introduce definition of this stability conditions on triangular category. But before that, let me talk about some motivations. There are actually several motivations for this concept. The more original one are from mathematical physics and homological mirror symmetry. But as I'm an algebraic geometry, so I don't understand. I don't quite understand the motivation from that side, and I don't want to pretend that I understand. So I'll talk about two motivations for this definition from the mathematical side. So the first motivation about this stability condition is from the so-called classical slope stability. Let me briefly recap this definition here. Here, the setup is let C to be a smooth curve, and let F to be a vector bundle. We can define the so-called slope of the vector bundle denoted by mu, and defined to be the ratio between the degree and the rank of the vector bundle. here the meaning of the rank is pretty clear. Just in case that you don't have any idea of this degree, yes, it just roughly tells you how positive of this vector bundle is. So in particular, giving you a line bundle, I hope you understand the degree of the line bundle. Just if it has a section, take a section, the number of the zeros and how positive of this line bundle is. It could be negative. And if the vector bundle, just write this vector bundle as some extensions of line bundles. It doesn't matter how you write it. And you take the degree of all of these line bundles and take the sum of all the degree. That's the degree of the vector bundle, right? That's roughly telling you how positive this vector bundle is, how many sections it can take. This is the slope. And the vector bundle is called a stable if for any non-trivial vector bundle, sub-vector bundle in this vector bundle denoted by E, the slope of the sub-vector bundle is less than the slope of the vector bundle F. In particular, we also have this semi-stable. In that case, we allow this equality here. The very quick example is when F is a line bundle, it's always stable because you have a subline bundle, it definitely have the smaller degree of this. No? And also, if you have some stable vector bundles and you take the direct sum of these stable bundles, it's automatically semi-stable because you can have one copy of them. And yeah, it can also build up some extension of the vector bundle with the same degree if they are still semi-stable. And that's the definition. So, and one of the nice properties for this, to give this definition, is we can always build up an arbitrary vector bundle on the curve by a collection of semi-stable vector bundles. This is how the HN filtration happens. So how to do that? So given a vector bundle, even if it's not semi-stable, we can choose the vector bundle with the largest slope, and then it's a sub-vector bundle and maps into this larger one. You can show that in that case, whenever the sub one is with the maximum degree, maximum slope, the quotient one is also a vector bundle. And then you take out this one with the largest slope, and then take out the second, and then so on and so forth, until you get something semi-stable that give you this filtration. And the factors are denoted here by EI, and one by one, the first one with the largest slope, and then you have this strictly decreasing chain of them. And you can finish this by final steps for trivial reasons because of rank itself decreasing. That's the definition of slope stability, and why it is very interesting, useful for algebraic geometry. Just I listed something, some facts here. One thing is helps, in some cases, it helps you to classify all of the vector bundles on the curve. For example, on P1, sorry, oops. Yeah, for P1, every bundle is a direct sum of some line bundles, and when the genus grows, the case becomes more complicated. For example, in the elliptic curve case, it's a result by Atiyah probably 70 or 80 years ago that of course can have more interesting vector bundles, but you can always write it as a direct sum of some semi-stable vector bundles. Another word to rephrase that is in the HM filtration for vector bundles on the curve, this filtration are all split. So, but that only holds for curves with very low degree, low genius, and the genius greater than equal to 2. The filtration could be very complicated, so it can never be split. One application, and the other is maybe the most important application is we can, given this stability definition, we can talk about we can define a good moduli space for good moduli space theory for vector models, sheaves. So you definitely have knowledge that given a curve is genus G, and all of the line bundles with degree 0, they form a space, naturally form a space which is an abelian variety of dimension G, but when you repeat the same story for vector bundles with rank 2, you can never get something so nice, because even in the P1 case, you get a dimension 2 vector bundle with the same degree. It could be, O plus O, say degree 0, O plus O, O minus 1 plus O minus O1, and you have infinitely many points separate from each other. So it's never good algebraic variety. But the reason for that is we included so many unstable stuff, like O1 plus O minus, that's destabilized by O1. So if we only allow the semi-stable things to come in, for all of these vector bundles with the fixed character, we can always parameterize it by a projective variety. And this is the moduli theory for curves, and that we also have a similar but slightly not so nice theory for moduli theories for coherent shifts on higher dimensional rank. And there we can also define this so-called slopes function given by this guy. So here, if you're not familiar with polarized variety, by that I just mean so this X is a smooth variety, and X give you an embedding of this X to some projective space, and the slope here is also defined to be the degree. This degree, if you haven't seen this notation before, I have no idea about it. It just roughly means you think this you take a in this case you take a subspace, a generic subspace, say with the correct dimension, with n small n to the dimension of x, p minus n plus 1, and take the intersection of these two guys. You got a curve. And also you can restrict this vector bundle on the curve. This guy, this HC Chen n minus 1f, is just the degree of this restricted vector bundle. Roughly still tell you how positive of this coherent sheaf or vector bundle is, but a little bit complicated than that in curve case. We have this, and we still have this moduli spaces. And in that case, moduli space is more interesting because when the variety is so-called Algebraic, namely the canonical divisor is trivial, there are a lot of interesting so-called counting problems. So, for example, if it's a Calabi-Yau threefold, I show that virtually the moduli space are always just finite collection of points. So it really makes sense to count the actual numbers of those points. And sometimes you really got some very, very meaningful numbers and huge numbers. In physics and even in mathematics, you can sometimes write those coefficient, write those numbers as coefficient of a power series. That's some very meaningful function. That's the story from this GW or DT theory. Classically, they count the moduli space of coherent sheaves, but nowadays people are more interested about word crossing problems. And when you do word crossing, so naturally the moduli space contains not only coherent sheaves but also some complexes of sheaves. So the problem now comes. If you think about this complex of sheaves, it's never an object in the coherent sheaf, in the coherent category, or any shift of it. So it can never be stable. It doesn't mathematically, it doesn't make sense to talk about they are semi-stable and include them as something to count. So the natural question raises this: is there a meaningful definition for stability on those more general objects, namely the complexes of sheaves? So that's the first motivation for stability condition. And the second motivation is about this so-called Hart structure. So by Hart structure, maybe the more standard the name for it is this T structure. And this problem, my personal problem and the problem of our field is we tend to call it Hart structure. So for that, I just also mean the heart and together with thing. If you know this, you know this, and don't know it, it doesn't matter. I don't know if I have any feeling of this, but an example in topology, but in algebraic, we have a lot of examples of the triangle category that the category have a very different hard structure. So that actually for any DB projective variety, you have very, very different hard structures. And the simplest one is when the variety is P1, that the result due to Bailinson, you can take the standard hard, which is just the coherent, the abelian category, give you this bounded direct category, and also can take this hard. Here I write it in this way, means the hard object are all generated by this O m homological shifted one and O m plus one. So namely, it contains all of the objects looking like O minus O m plus one, O m plus two, and all of the line bundles is degree higher than the m, and also all of the line bundles degree less than or equal to m with homological shift. All right. And also have skyscraper shift here, all contained in this in hard, and of course you can take a direct sum of them, and that's you can check that's my hard. And for any m, we have this kind of construction. You can make this hard a little bit more crazy, but that's one class of the examples. But here you can see it seems in this example, some hard are seemingly closer than the others. I mean, if here is O0 is O0 shift one, O0 shift one, O1 is closer to O1, O2 rather than like O100 or O101. So it seems they have some kind of distance between each other. But without in this example, they are still very, very discrete. But somehow one can be created to ask, if I take all of the different hard structure on this triangle category, possibly I need this hard to be very nice. Is there a good topological structure on the collection of all of them? That's another motivation, right? Given those two motivations, of course, as explained, this is not the original motivation. Actually, it's just some mathematical algebraic geometers hope before this concept was introduced. We can see this the definition of stability conditions, which solve the questions that we asked in the previous slides. So what is the stability condition? So the setup is we have this triangle category. It's a very arbitrary triangle category. Just need to be C-linear. Actually, even the C-linear restraint can be relaxed a little bit. But here for me, my examples are all cold. So it's C-linear. The stability condition is a pair of datum. One is the very classical stuff. It's the bounded hard structure. Here, by hard structure, I explain it means T structure. Also, I hope you already know this thing. And bounded, that just means every object can be written down as every object is homotopic to a bounded complex. Or every object can be built up by finitely many objects in the hard with homological shift. That's a bounded mean. I hope that's not a disaster restriction for topology. I think a lot of examples are not bounded, but in my case, this DB code by definition is bounded. The bounded hard structure, and also is that sometimes they call this the official name for this is central chart, which I'll keep speaking for the rest of the talk. Is that a central chart? And naively, you can also think that's the classical slope function on the hard. So here it is z white is the slope function because that here maps k numerical to c. It just means it factor y or factor 2y. It's kind of hard to distinguish. It actually maps all the objects in T to C. But this map factor via this K num. So with the same character, macro character, the same object goes to the same complex number. And that is is a map to a complex number as the real part and the imaginary part. And equivalent, you can define a slope, an actual slope function for objects in this category. It's just defined to be something like that. So naively speaking, so there are some requirement on the heart. It maps. So first of all, it maps this objects in the heart to the strict upper half plane together with the negative real axis, something on the top. And removing the origin, that's important. To compare this the slope with the central charge or the slope function as the slope is defined with the same with some comparison with the augment of the central charge. So if you think about this expression, so an object with a smaller slope, it is with the smaller augment of the central charge. So when the slope is going up, the augment of the central charge of it is going anti-clockwise. Something like that. So you see that the central charge maps those objects on this upper half plane in this way. So you can have morphisms from objects from the right hand side to the left hand side. You cannot. There's no morphism from the object with larger slope to the object with smaller slope. You can never have maps from the left to the right, right? And it has to satisfy this H infiltration property. So every object in the heart, it can be built up like the slopes to the case by objects with larger slope to objects with smaller slope. And there's another technical property I don't want to explain more. Support condition, very important for us who's doing this subject, but it's not very useful for the audiences. Sometimes they bring a lot of nasty to our research. Right. So here's a definition. We need to see a example right now, and the example is given by this classical one. The C is a projective curve, a smooth projective curve. We take the dB curve of it. We can just take the standard heart on this curve, okay? And also the classical slope slope function. So here the real part is minus degree. So take the minus of real over the imaginary. So it's just the degree over the rank. That's mu is. And not very hard to show that it's indeed a stability condition on this one on the triangle category of that. And now we need to so this is one definition, and we to make the talk go on, we need to give an equivalent definition of it. To do that, let's rethink about this. What does it mean for a hard structure on triangle? This is my cartoon for a hard structure. Cartoon here. This is the hard structure for a triangle category in my mind. So what a hard structure is, just like cutting this whole triangle bounded hard structure, cutting this whole triangle category into boxes. A box of this box containing all of the objects in the heart, containing all of the objects with homomorphism 1, so on and so forth. And the property of that is you may have morphisms between objects in the heart. Can go this way, go that way, and also you can have morphism from objects between boxes, but you can only have, so this is the so-called look right property. So you can only have objects from the box on the left-hand side to the box on the right-hand side, but you can never go back. So an object can never have a morphism from this higher shift to a lower shift. So let's look right and then look left. So that means the whole category built up by this Hart structure. So for any non-zero object, you can filterize this object by objects from the Hart with a homological shift, right? So you can for any object in T, you can always filterize this by factors and by Feynman steps. These factors give you, roughly speaking, build up this F. Just think about writing as complexes and then and naively like that, and you can figure out this is that's exactly what this HN filtration of a stable object did for objects contained in this Hart. So how to think about how to realize that is we consider the category this as defined by p theta to be all of the semi-stable objects in the Hart with the corresponding slope. So I rescale the slope. So now before that the slope is from minus infinity to positive infinity. Now I rescale it so that the slope is just from 0 to 1. And for each of p theta, I can think them as a slice in this box. Right, that's right, p theta, like 1 p theta 2, and still it keeps the property of this Hart structure. So you may have morphism from this p theta 1 to p theta 2 for objects with a smaller slope to larger slope. That's allowed, but you can never have morphism for objects in this guy with larger slope to smaller slope. So you can never have arrows from the right to the left. So previously the Hart structure is kind of a structure, a Z structure. You cut this whole category into Z boxes like that. And this by giving this actual slope function, you can cut this into the so-called finer structure. Finer slicing, so that the whole thing, the whole triangle category is cut into R slices, right? So that's the P theta given. Also, the central charge, the compatibility of the central charge is more clear. So the central charge maps the slicing object in each slice to a real ray with the correct augment or angle, whatever you like. And when the object goes to, when you look at object in this slicing goes from 0, say -1 to 1, it rotates this the central charge of this object rotate along this complex plane by 1 circle, right? And this is the slicing. And actually, given this concept, we can combine this HN filtration, the property of the HN filtration and this Hart structure property together to give an equivalent definition of this stability continuum, which is actually the more original definition, which is right here. So so you can replace the HN, combined HN and Hart structure together as this concept of sliding, which I explained. There's no morphism from objects with larger slope to smaller slope, and everything can be built up by objects with larger slope to smaller slope, and also have to compatible, like the Hart structure, compatible with this original homological shift. And also this slicing has to compatible with the central charge, which is right there. So now I can combine this together to rewrite the stability condition as a pair of slicing and a central charge. And also the only thing missing here is the support property. I have also to include it here as the equivalent definition, which is actually the original definition in the paper. And the reason we have to go to this equivalent definition or the original definition is that only in that way we can define clearly define two important group action on the whole set of stability conditions. Oh, of course, I forgot one thing is so there's a given definition of stability condition. There, given a triangle category and definition of stability condition, there could be actually infinitely many stability conditions on a given triangle category, and we denote the set of them by the stability. The set of objects in each of the object is an element, and each of the element is a stability condition. And there are two natural group actions on it. One is by this one is the C action. Actually, it's a 2R action. So how can I take action on it? Maybe it's better to go back to the slicing picture. So here are the slice, and we cut. We slice this triangle category into R slices, so you can shift the whole thing by an arbitrary real value of by an arbitrary real number. Namely, given a hard structure, you can just shift everything by a homological shift. But here, since I cut it in the finer pieces, you can shift it by any arbitrary real number, and accordingly, shift everything in this slice by 1/2, and shift everything here by 1/2, and then so on and so forth. So it's still, by definition, it doesn't change anything. It's still sliding on the whole category, and also the only thing you need to change to make the whole thing compatible is the central charge. So you also rotate the central charge by like a 90 degree if you shifted the sliding by 1/2. So this is one of the action by the real values labeled as A. Here, and another thing you can, given that you can also rescale without changing the slicing, you can rescale the whole rescale the whole central charge just by timing the central charge by a fixed positive number. It's still a central charge compatible with the slicing with the change angle. That's the BI. Just rescale the central charge. So together they give you a C action on it, and this action is acting from the right track. And also for any automorphism, autoequivalence of on the triangle category, naturally induced an action. It also gives you a new stability condition. Actually, use action on the whole space of stability condition. That's fairly easy to understand. But one thing to remark here is this action is acting from the left. So this C is acting from the right, and the other is acting from the left. So they commute very well with each other. And this is the group action. And also we we can, given this slide, you can define here a topology on the whole space of stability conditions. Actually, there's a generalized distance function in the sense that for any slice, for any two slidings, we define the distance to be we sort of run we check all of the non-zero objects in this third category and compare and look at their Hn filtration, compare the phase of them, and take the difference of the maximum phase, take the difference of the minimum phase, and take the theorem of all of the objects and all of the filtration. Actually, you can show that you only need to check all of the stable objects in one slice. So it's something really doable. That's distance function on the slicing is really a disaster. But we will see later on that it's not that useful because you can throw it away in the future. And also then you can define this distance function on the space of all stability conditions to be the maximum of the distance of slicings and the norm, the distance between their central charge. But here, recall that the central charge is just the group homomorphism from K num to C, which as a space is isomorphic to C It's just a finite dimensional. And sorry, here I assume this k num is finite for simplicity. You can actually do some trick to treat with the infinite case, but here just assume it's finite. So something like that. But anyway, it's just a complex dimensional space. You can define any equivalent norm on it to give you a distance. But that's not important, you'll see pretty soon. So that gives you a distance function, or give you a topology on the whole space of Stability conditions. And the biggest result, in this to set up this whole theory is now if I take the forgetful function, so every stability condition has two pieces, the sliding or the hard structure and central charge. I take the forgetful function, only remember the central charge, which is something contained in this vector space, finite dimensional vector space. And this map, given the topology I just talked about, this is a local homeomorphism. So in other words, for any points on this space of stability condition, you can have a local chart of complex structures for it in its neighborhood, and that gives you this complex manifold structure on the whole space of stability conditions, which will still denoted by step T. And we also know, locally, that's always isomorphic to some open subset of this C with dimension rank of the numerical gross-integer group of the triangle category. So it's a complex manifold with this dimension, which is not very hard to compute for any given triangle category. Another thing to say, you'll probably also use in the future is, there's a natural, we call this natural C action on the slicing and slice and slicing central charge on the stability manifold. It naturally you have this rescaling and rotation on the space of central charge has this C star action on the space of all central charge, roughly given like this. So it's well defined, and also this forgetful function reduces to forgetful function of this quotient manifold. And one thing I forgot to mention is the C action is easy to check. It's a free action. So so when we are talking about stability manifold, sometimes we secretly mean this guy, and which and when we talk about forgetful function, I also denoted by this forgetful. So in the future of the talk, I'll probably use this without noting that. Right. So this is the main result 20 years ago, and from what can we do from there? And the next question about this space is what's the property of this stability manifold? The meta conjecture is this. So given for this for DB coherent X, we denote the whole stability manifold by step X. The meta conjecture is maybe it's a little bit too ambitious. It's a non-empty and contractible. It's a little bit, maybe it's an ambition in the sense that there's just no counterexamples to this conjecture, but people are not actually hoping to prove this such a so strong thing. Most interesting case is when this X is so-called Kang-Bi-Yao, namely canonical divisor is trivial. Originally, about 15 years ago, the conjecture was only made for K3 surface. I hope you know what it is. It's fourfold, and I think most of you may be familiar with this because of the 11/8 conjecture, and that's the same K3 surface, I think. I read this topologically, but we have a complex structure, so we may have different complex structure on them. And this step K3 is a conjecture to be connected and simply connected. And that's not only because of curiosity, it's something nice to conjecture, but also this result has some very, very interesting correlates. We will see pretty soon in the next few slides. And also another thing is the reasons for one of the reasons for that is when it's Kang-Bi-Yao, in particular this K3 is Kang-Bi-Yao, this quotient space is expected to be very interesting, and this whenever it shows step case arrays connecting simply connected, and this is the universal cover of this very interesting space. And pi1 of that, you can read clearly from some part of the orthomorphism group of this bounded derived category. And here, and this is a remark on this meta conjecture we'll discuss in the next few slides. And here's also another question by my own. So this is my personal hope. I hope someday the miracle can happen. We can get some very good some function like thing on the whole stability manifold. Just depend on the property of the triangle category, so that it tells you directly that this whole space is non-empty and contractible. I mean, you hope that sometimes you do math pretty easy. You just throw a random question and hope that the God can tell you the answer directly, right? I don't know if you guys doing topology use this trick, but here I'm just throwing this random question and hope some miracle can happen. Right? So here's somehow the main question on this stability manifold, and we'll see some more concrete examples in the next few slides. Now here's one remark about the before going to the stability manifold. Here's one more remark. Here I said that it's contracted two parts. One is non-empty, and the other is contractible. I want to emphasize one thing is that actually the non-empty is already very non-trivial. For example, if you just yeah, there are metrics. There are a lot of I can also define a lot of metric on this, or metrics on categories. I don't know that. I don't know. Yeah. Okay, thank you. I have no idea about that area. I'll try to look it up. Thank you very much.
Okay, yeah, let's thank the speaker.
No, sorry. Oh,
is it done? Oh, sorry. Oh, sorry. I misunderstand. Sorry.
All right. That's pretty cool. Okay, so it seems everyone's lost though, so I can speak random. Sorry, I'm not going to finish by a random question. I still half of the slides come there, so I'll be quick. So one remark is about the existence of a stability condition. So non-trivial question. For example, you just do naive things for stability condition on a surface, always surface, you just simply failed. The reason for that, we use the standard heart, standard another question. Standard and standard slope function. The problem of that is that it maps the so-called sky sweepership to 0. You can standard call any information chain 2. OP has chain 1, both chain 1 rank 0, chain 2 1. So it's mapped to 0 by this classical slope function. So it cannot be a stability function. And actually you can prove that if you just naively take the standard heart on the surface, you can never construct a stability condition. You never have a slope function in the sense of Bridgeland, because it requires some strong condition, mapping all the heart, avoiding the 0. That's the reason. So to construct an actual stability condition on the surface is already a non-trivial thing. We use the so-called computing thing. I don't want to explain the details because I want to talk about something more, some other thing about the stability manifold. Anyway, it's complicated, and we have this finally. We can do this construction, and we have this standard slice. Especially remember this formula, written like this twisted chain character form. You'll see that in the future many times. It's a hard story, and also I give a list of manifold that the stability manifold, the complex variety that stability manifold is known to be non-empty. They include all of the curves and all of the surfaces. And in the threefold case, already non-trivial, we have all of unknown threefolds. We have a some copy of threefold, maybe most interesting one of Bailin, Kuntik are there, and a few others. And also we have some stability conditions. The derived category is relatively easy, not because of their dimension, but just because of the derived category. Like this Pn and quadrics cubic fourfold can have a relatively singular so-called semi-orthogonal decomposition. The Pn can be composed as line bundles, the Bailin theory, and also there are this. I mean, the list of this example is very long. You can have Grassmannings here. You can have quadric fibrations here. Whenever the base of the quadric fibration is known to have stability condition, or you can have a root variety here. Whenever the base of that can have a stability condition, and always write on the semi-orthogonal decomposition and build up stability condition on each pieces and glue them together. Have all theory. And also, there's a theory not long ago by sorry, lost my pen. By Yu Cheng. I do want to write a name because it's on the stock market, and so I do want to throw some credit at this point. So his result reading like this. So whenever we have a you know there's stability condition on X, you can construct stability condition on the product of this variety with the curve. That will be also very important for our example in the final slices. This is about existence. Now about the stability manifold. We see this example of curve. In this case, it's pretty easy. We can completely solve the questions by following steps without too much difficulties. First, in the curve case, because global dimension 1, every object completely splits as object with homological shift. There are no interesting complex there. And also we can show that all of the line bundles, all of the line here, right, the structure sheaf for the trivial line bundle, and the skyscraper sheaves are stable. And the stability conditions are determined by the phase and central charge on two of them. Here you can take the structure sheaf and a skyscraper sheaf, or you can take a line bundle with degree other than 0. And by using the only restriction for the central charge on them is the phase, because we have mapped from OC to OP, and by standard derivative OP to OC should be by 1. So we should have this relation between their phases to make there's no contradiction. That's the only restriction. And by the C action, we can rotate and rescale the phase of OP to 1 and the central charge to be -1 on the negative real axis. And that given this constraint, we have this OC must be lying, the central charge of the OC must be lying on the strict upper half plane. So so now everything is done by making this C action. We can always make the central charge of it to the upper half plane and easily show that everything is decided by this information. You show that's the range for this C times H. Where C is the free action in general we don't care about. So modulo C is just the upper half plane H. This whole stability manifold. And also I want to mention here this H is also in this case the standard slice of stability condition denoted by this twisted. The notation will be important in the future. I don't want to go to details. One very interesting case is, as explained, when the surface, when the curve is Capial, namely in this case it's an elliptic curve. Now, why it's interesting, because we have a lot of interesting autoequivalences on the derived category, not only from the autoequivalences of the curve and on the coherent sheaves, which are tensor line bundles, but we also have, this guy, everyone have the homological shift. Also not so interesting. But in this case, I have this very interesting so-called spherical twist. And I don't want to unpack the details of it, but just letting you know that it has some non-trivial action on the stability manifold H, which can be described as it maps interpret the coordinate, and maps this Z to Z over 1 minus Z. And together with this tensor Z maps just by a shift of the lattice, those two guys actually generates this classical PSL to that action on this upper half plane, and you definitely know this is taking the whole thing. This thing is actually the space of all the modular forms. Right? That's the curve. Another thing to mention here is the projective line. So for all the other curves, they are less interesting because they don't have the spherical twist. So the whole thing, and it's also expected they are less interesting for some reason, but also I just mentioned that without explaining. And also for this P1, the P1 is more complicated in some sense here. Compared to other curves, it has more specific conditions because, say for example, the structure shape and the skyscraper shape can be non-stable, but people still can describe it in some way, since that by the theorem that for any specific condition, we must have some m such that both OM and OM plus 1 are both stable. So we can write as UM to be the open subset of all of the specific conditions, such that both those two guys are stable. So union of them is the whole space. Here, the intersection of them is also interesting, containing all of the specific conditions that skyscraper. The points are stable, and the whole space is the whole space. You should do some analysis here and show that it's C2, and obviously it's as a complex manifold, as a topological space, it's the same as Euro curve, but as a complex manifold, it's different. And there are also some general conjecture for this to be manifold with which admits so-called full exceptional correction at the case of P curve surface. Those are the only cases we know. Cases of surface that we know the whole stability conditions or a component of stability conditions. In all of the cases, there is P2 available component, but in all cases we know they are contractible. The most interesting case, let's give some words, is the K3 surface case, because like the case of elliptic curve, it also has a very, very interesting autoequivalence group on the bounded derived category, for which besides the thing we come from the category of the coherent sheaf, but also we have a lot of the so-called spherical twist. Even classically, this group is not understood very well yet, but then like the case of elliptic curve, for which the autoequivalent group is already very well understood. For the K3 curve surface case, we only know it has this generating sets of this spherical twist, but people have no idea about the relation of the sphericals at all. And with the only exception that when K3 is generic, namely K3 is of Picard number 1, that's the only case this conjecture is solved. People understand what actually happened here. And the next slide is a cartoon trying to explain that. So here we have this cartoon, this orange part, by removing all of its bullets. Actually, there are infinite bullets in each intervals, but I couldn't draw on this picture clearly. But if I have infinite many bullet points corresponding to each of them correspond to so-called spherical object or spherical vector bundles on this surface. And there's a very complete numerical description for all of them. Like spherical bundle is just taking the Euler character itself. It's true. It's numerical, fully numerical descriptions telling you the position of all these spherical objects. And this thing is the orange thing, removing all of these bullet points, as just the interesting the actual slice telling you that the fundamental group of the quotient space that I mentioned before, in this as the image of the Fugate functor in the space of central charges. So namely, if you lift it, the space of the stability manifold it will be a universal cover to the space here, And direct corollary of that is the pi one of this guy. And actually, I missed the homological shift 2 here. So dark sum over. I don't know the better notation here maybe. And this is the interesting part of the autoequivalent group on the whole derived category of K3 surface. And from this total picture, you can see that this pi one of that is the free group generated by all of the spheral twists corresponding to those bullets, which are strictly speaking written like this. And in particular, all of the in particular all of the spheral twist, the double of the spheral twist has no relation with each other. They're completely free, right? This is a rushy explanation for the story of K3. And then I will finish talk by the three-dimensional case. In that case, we know much fewer, because even for most of the cases, the stability manifold is not known to be non-empty. But still, we're very lucky that in one case we know the whole stability manifold. That's the Abelian threefold is beaker number 1. And also we have some conjectures for the cases when the varieties copy out, and those two are the main ones I thought most interesting. The first is when in the case of a smooth quintic threefold, the so-called stability manifold quotient space as a conjecture contains so-called something from the mirror symmetry, the stringy Kähler moduli space. I'll show you a picture what roughly it means. And also in the Abelian threefold case, but it has a much higher Picard group. This has a precise conjecture of what it looked like. So here, this two term is the universal cover, and this is something with the complete linear algebra description. We can't solve any of the conjecture, but we have made some progress. For example, the one told the smooth quintic one. So this picture of scoping is this whole thing as the stringy Kähler as I draw in the last slides. This MK. This is the MK. It has 5 pieces. Has this highly stacky point here, which is called capital point. And what we know is what we can construct. We have the stability conditions on this green shaded area. So it contains important points, so-called large volume limit, and also contains so-called conical point. And you still remember we have a standard slice of stability condition, but the area of that is something here. So we can't construct all the standard slice stability condition, but due to some technical reason, but the gap is very, very small. And most difficult part is to construct stability condition here or add this capital one, which is still unknown for technical reason. That's the story of quintics. And the story for Abelian threefold, we have this new results very close to the original conjecture. So we can't show it has the space is that we can show that there's an injective map between from the stability manifold to the space conjectured by Kontsevich and Fabian Hayden. Roughly speaking, the theorem we prove is that, and we have a very nice corollary of this new result as by combining the BKR, so-called BKR equivalence. We know 20 years ago, people know 20 years ago, and some technical result on the reduction of stability condition by this G equivariant derived categories, we can construct a standard family of stability conditions on the Hilbert scheme of any points on the K3 surface, which is also very interesting higher dimensional Calabi-Yau variety. And I think it's good to. I'm sorry that I'm quite rushed at the end of the talk, but it's good to stop on time. And thank you for your attention. And feel free to ask questions.
Yeah. Thanks for the speaker. Yeah, I'm very sorry. I just misunderstand. Yeah, just misunderstand the thing. Sorry. I'm very sorry. So, yeah. Any question? Yeah, if you have any question, you can directly unmute by yourself. I'll see it in the chatting. Okay, yeah, probably I have a question. So is there a Bridgeland stability condition theory on the derived category of D models?
And there should be. There should be.
Okay.
It should be, but we have to work hard to work out details. The problem, I think the problem for D modules is about the K group. First problem of that is the K group. Yeah.
Oh, okay.
We have an understanding of so the definition I gave here is a little bit cheaty. I mean, you can relax the condition. You can relax this via K num to K0. but that may be helpful for D modules. But that's the first thing you need to do if you really want to consider that question.
Okay. Okay. Thanks. So, any other question? Okay. So if there is no question, yeah, let's thank the speakers again. Okay, so tomorrow we will start at 8. Hopefully to see you tomorrow.